welcome to this lecture series of optical instrumentation. This is 7th lecture of this series, and in this lecture we shall discuss about lasers. Till now we have discussed in second unit, we have discussed about LEDs, we have started light sources, and under light sources we have already discussed LED in our last lecture, and in this lecture we shall discuss about lasers. Okay. So, in this lecture we will be discussing about lasers, then stimulated emission, a principle that is used to generate laser light, then a derivation on Einstein's relations, and after that we shall discuss population inversion. Okay. So, what is laser? This is not a very new topic. In your earlier classes, I am sure you must know what is laser. The full form of laser is light amplification by stimulated emission of radiations. So, light amplification, this name contains various technical terms. First is the light that we get from laser is amplified. How it is amplified? By a process, a phenomena that is called stimulated emission of radiations. Okay. So, before we move further and discuss about lasers, we must know why we are studying lasers. There are certain properties that are of our interest about lasers. The light that we get from laser is highly monochromatic. It is coherent and it has directional properties. Now, what is monochromatic? The light of single wavelength. White light we know is a combination of 7 colors and a range of wavelength is inside it, and we need monochromatic light, single wavelength light in various processes. In laboratory, in research, we need monochromatic light, light of single wavelength. So, the light that we get from laser is highly monochromatic. It depends on the material which we use to generate laser, that which wavelength we get, but we get highly monochromatic light. In various optical instruments, monochromators are used to get a light of single wavelength. To convert white light or to convert a light of multiple wavelengths into single wavelength. Slits are generally used for this with prism and grating. We shall discuss these things in unit number 3. Also, coherent. Laser is a coherent light source. In first unit we discussed what is coherent and incoherent light source. Okay. The light sources that are of almost same amplitude with 0 frequency difference, 0 path difference, they are coherent light sources. To generate diffraction pattern, to generate clear interference patterns, we need coherent light sources. Okay. And third one is directionality. What is directionality? We can focus a huge amount of energy in a very small area, directionality. If you have seen those toy laser lights, you must know that it does not diverge. You can see a beam of light traveling and it does not diverge at all. So, it is highly directional. It can go up to kilometers in a very small area. So, it has various use in medicine, in medical field, in industrial applications, in research applications. Lasers are used everywhere. These days lasers are used for operating a human being, also for cutting metal in industries, because we can focus a huge amount of energy into a very small area. Due to these properties, lasers are very extensively used in all the fields. Okay. So, let us move ahead and understand how laser works, what is the basic principle, basic phenomena of stimulated emission. Okay. For this, we shall discuss about two phenomena, that is absorption and emission of radiation by matter. We know that material can absorb radiations, electromagnetic radiations, and they can also emit electromagnetic radiations. So, we shall discuss these topics with the help of these diagrams. So, this is the process of absorption. Okay. This is the process of absorption. So, as you can see, this is a lower energy level of any atom, let us say ground state or even state, and there is an electron in its ground state. What happens when a photon of energy h nu strikes on this electron? The energy of the photon is absorbed by the electron, and if this energy okay. So, a photon of energy h nu is striking on this electron that is in the ground state. If this h nu is greater than, let us suppose this is higher energy state, its energy is E2, and this is ground state, energy is E1. If h nu is greater than or equal to E2 minus E1, right? We know this condition. If energy of this photon is either greater than or equal to the difference of the energy of these two energy states, E2 minus E1, then what will happen? This energy is absorbed by this electron, and this electron will jump in E2 state, in excited state, and it is called excited electron, and this process is called absorption. This process, what it is called? Absorption. Absorption, because radiations are absorbed by the electron. Fine. Now, what happens after an electron goes to excited state? It remains there in the excited state for a fixed time, and after that time it jumps again to its ground state. Normally, this time is 10 to the power minus 8 seconds, right? We all know this from 10 plus 2 physics. So, what happens? This electron will remain in excited state for this much amount of time if it is a normal state, and if this state is a metastable state, then it can remain there for a longer period. Okay. So, after 10 to the power minus 8 seconds, the photon will again jump to ground state, and when it jumps to from excited state to ground state, it will emit a photon of energy exactly E2 minus E1. So, how much is the energy of this photon? Exactly equal to the difference of the energies of these two states. So, for example, the energy of this state is E2, the energy of this ground state is E1. So, E2 minus E1 is the energy of this photon. Remember, this photon can be of greater energy, more energy than E2 minus E1. Then what will happen? The remaining energy will be emitted in another form, in either heat. Okay. So, the energy of this photon is E2 minus E1, and if this energy h nu is such that the frequency is in the visible region, then we can see this photon. This process is called spontaneous emission. Okay? Spontaneous emission. So, emission is of two types, one is spontaneous emission and second is stimulated emission that we need for lasing action, to perform lasing action. Now, third is stimulated emission. Now, what is stimulated emission? We are interested in this particular phenomena, stimulated emission. So, this electron is in the excited state, it has absorbed some radiation and it is in the excited state. While this electron is in the excited state and before it jumps on the ground state, if a photon of energy h nu, and this h nu must be equal to E2 minus E1, if the photon of energy h nu, this is E2, this is E1, strikes on this electron. Okay. So, this photon of energy E2 minus E1 is striking on this electron, then what will happen? This electron will jump to the ground state before this time. This time is not expired, this time is not completed, but before this time has expired, a photon, another photon has struck this electron and this energy of this photon is exactly equal to E2 minus E1. So, due to this what will happen? This electron will jump to ground state and it will emit 2 photons. How much? 2 photons, and the energy of these 2 photons is exactly equal to h nu, that is E2 minus E1, E2 minus E1, the energy, that is the energy of incoming photon. Okay. So, from one photon of energy h nu, we are getting 2 photons of energy h nu. These 2 photons are highly coherent, they have same wavelength, they have same frequency. Why? Because energy is same, h nu. Okay. So, they have exactly same frequency, they have exactly same wavelength, they are monochromatic and they are highly coherent. Now, what will happen if these 2 photons find 2 more electrons in excited state, then they will perform same action of stimulated emission and we get 4 photons of energy h nu. From 4 we get 8, 16, 32 and in this way these photons of energy h nu will get multiplied, will get amplified. That is why the name light amplification by stimulated emission, okay, of radiation. For this special arrangements are made, cavities are used, the material is placed inside that cavity. We shall see the operation of lasers in later lectures. Okay. So, now we shall understand what is absorption, what is spontaneous emission and what is stimulated emission. To perform lasing action, we need all these phenomena: absorption, spontaneous emission and stimulated emission. But what we need? We need stimulated emission more. Okay. Now, to perform stimulated emission, we know that more electrons should be in excited state. We have to achieve this condition inside the material that we will use to generate laser. We need more electrons in excited state or we need more atoms in excited state. Generally, we know that in ground state there are more number of atoms and in excited state there are less number of atoms. But we need opposite condition, we need more photons in excited state. This state in which the number of photons in excited state is more than the number of photons in ground state is called population inversion. We shall discuss that phenomena later. Okay. So, let us move on and discuss Einstein relations. Okay. So, let us consider that n number of photons are incoming on a particular volume of energy h nu. Okay. So, let n number of photons, n is the number of photons of energy h nu per unit volume. Then how much is the energy density? What is the energy density? Number of photons per unit volume into energy of a single photon. So, this is energy density and we are denoting it with rho. Okay. So, rho is equal to n into h nu. Now, if let us consider that in ground state number of electrons are n1. Okay. n1 is the number of electrons in even energy level. What is this energy level? This is ground state. Then upward transition rate, absorption rate, how much photon will be absorbed and how much electron will move to ground state to higher state. So, electrons are moving from ground state to higher state, we are calling it as upward transition. So, upward transition rate will depend on two things. One, energy density, how much photons are coming on the material, more number of photons will come, more number of electrons will absorb photons and more number of electrons will get excited. So, upward transition will depend on energy density and the number of electrons in ground state. How much electrons are there in ground state? If there are more number of electrons in ground state, then upward transition rate will be more in presence of sufficient photons. If number of electrons in ground state are very less, then upward transition rate will be less no matter how many photons are there. Okay. So, rate of upward transition can be written as n1 number of electrons in ground state rho, that is energy density, and into B12 where this B12 is a constant. Okay. Similarly, downward transition rate will depend on two things. Number of electrons in excited state, that is N2, let us consider N2 are the number of electrons in excited state, that is we are calling energy level E2 per unit volume. Okay. So, stimulated emission rate will depend on number of electrons in excited state and number of photons of correct energy that are available. What is the correct energy? E2 minus E1. Okay. How many photons are available for stimulated emission? Because for stimulated emission we need photons of correct energy. Downward transition rate from level 2 to level 1 will depend on number of electrons in excited state into energy density rho into a constant B21. Again B21 is a constant. Now, this was downward transition due to stimulated emission. Now, downward transition due to spontaneous emission. There will be spontaneous emission also, right. Some electrons will jump from excited state to ground state due to spontaneous emission because their time expires. The spontaneous emission transition rate from level 2 to level 1 will depend only on number of electrons in excited state. It will not depend on energy density, okay, because for spontaneous emission we do not need a photon. it will automatically jump from excited state to ground state, okay, and into a constant A21. So, total downward transition rate is downward transition due to stimulated emission plus downward transition due to spontaneous emission. Okay. These three constants, they are called Einstein coefficients, and we have to find out the relationship between these coefficients. Okay. Now, for a system that is in thermal equilibrium, the rate of upward transition is equal to the rate of downward transition. Okay. So, this is the rate of upward transition and this is the total rate of downward transition. So, N1 rho B12 is equal to N2 rho B21 plus N2 A21. Now, what we have to rearrange it, we can rearrange it, and this term will come over this side and we will take rho common, and by rearranging we will get this. Rho is equal to N2 A21 divided by N1 B12 minus N2 B21. We divide numerator and denominator by this term. Okay. So, in numerator we get A21 divided by B21 and in denominator we get this term. Okay. Now, next, in thermal equilibrium, the population of two energy levels of the system is given by Boltzmann statistics. And what is that? N1 divided by N2, population of electrons in N1 state, population of electrons in N2 state. If the system is in equilibrium, N1 divided by N2 is equal to G1 exponential minus E1 by kT divided by G2 exponential minus E2 by kT. So, we can also rearrange this. What is this? This is G1 e to the power E2 minus E1 divided by kT. Okay. We can write it like this also, divided by G2. Okay. Because when we exponential minus E2 by kT, we take it in the numerator, this minus will go and we can take kT common. So, E2 minus E1. So, what is E2 minus E1? E2 minus E1 is simply h nu. Okay. So, we can also write it N1 divided by N2 is equal to G1 by G2 exponential h nu by kT. Okay. Now, we have to substitute this value of N1 divided by N2 into equation 3. Okay. What was equation 3? This one. Over here we have to substitute N1 divided by N2. Okay. So, G1 B12 divided by G2 B21 exponential h nu by kT minus 1. This is equation 5. Fine. Now, again, in thermal equilibrium, condition of atoms must give rise to radiation which is identical to black body radiation, and the equation for energy density of black body radiation is this: rho is equal to 8 pi h nu cube divided by c cube 1 upon exponential h nu by kT minus 1. So, we have to compare this equation 6 with equation 5 and we will get relationship between these coefficients. So, as we can see, you can easily compare. This term is equal to unity. Over here there is 1. So, G1 B12 divided by G2 B21 is equal to 1. So, that is why this is first Einstein relation. Okay. And A21 divided by B21 is equal to this term. A21 divided by B21 is equal to this. So, this is equation 7 and equation 8. So, equation 7 and equation 8 are referred as Einstein's relations. Okay. Equation 8 enables us to evaluate the ratio of the rate of spontaneous emission to stimulated emission for a given wavelength of light, for a given pair of energy levels. Okay. So, with this equation we can find out the ratio of spontaneous emission. What is this? This is constant for spontaneous emission and this is constant for stimulated emission. So, we can find out the ratio of spontaneous emission to stimulated emission using this relation, okay, for a given pair of energy levels. Fine. So, this was Einstein's relations, equation 7 and equation 8. G1 and G2 are called level of degeneracies, While going for energy level E3 and E4, there are bunch of energy levels, they are a combination of energy levels, and this is seen by the level of degeneracy, G1 and G2. Okay. So, next after this we shall discuss about population inversion. Okay. So, population inversion we will be discussing in next lecture. Okay. Thank you.